finite element analysts need to know a little about convergence, because this is a process where you improve the model and then get better and better answers. Sometimes convergence is based on concepts dealing with the mesh size, or sometimes it's done with the refinement of the polynomial degree. Finally, you can also improve the quality of the mesh as time goes on in your modeling process. So through some combination of these refinement ideas, you arrive at a model that's suitably accurate for your needs. I'm going to start out with some convergence concepts. These are simple ideas about how models are improved, and then I'd like to use a small industrial case study on a jet engine where a group had to do their own simple convergence tests, and then we'll end up with several problems. Years ago in mathematics classes, I was interested in the idea of convergence of series. And here you found that there were two ways to look at it. One way was to think in terms of what was called Cauchy convergence, and that had to do with looking at the change between successive terms in a sequence, or as they were summed up into a series. For instance, your baseline value might be this lower left point, and then some refined model in some way, perhaps judging by the number of degrees of freedom in the model, might move you to this second point on a quantity such as stress, strain, displacement on the ordinate here. And the difference between your current value and the previous value would be reflected by this bracketed quantity here. And that then, as you track it from refinement to refinement, going to this third point would give you this small bracketed quantity, and then lastly this would give you this very small amount. And by comparing the change of those quantities, which are they're not quite errors in a sense, they're just changes from the last solution to the current one, you would get some impression of convergence, and Cauchy gave some rules under which you could prove that that sequence of numbers would converge to a finite number. But what would be better if you were able to do it would be able to compare your current answer, say this baseline, with some absolute value that you know to be the correct value. Then as you progress along here, you would generate these blue braced quantities, and here's another blue brace that's a little smaller, and then finally a smaller one, and that would be called absolute convergence. And there are some rules on that for convergence also that you can find in the elementary textbooks. So whether you could get absolute convergence or Cauchy depends on your situation. But unfortunately, most of us in the finite element world really deal with what you might call Cauchy convergence, where we want to do several refinements in our model and then observe the change in the answer as we move along. If the system is really complicated, we're not going to know the absolute value, and we can't use absolute arguments. Remember, Cauchy sequences, for instance, if the numbers are changing by 1 over, let's say, n, and that might be some residual quantity here of the change each time, then that doesn't converge. On the other hand, if the terms vary as 1 over n squared, then you do get convergence. So those are rough concepts. The convergence ideas that we're working with here depend on looking at a sequence of finite element models and then making a better and better model. Now, this isn't really done in practice very often. It's usually done at the beginning of some product analysis where, whether it's a wheel or an airplane wing, the analyst will determine what mesh quality is needed to get a reasonable answer. But after that, generally as subsequent analyses are done, they're done with that convergence quality built into their thinking and influencing the mesh size and the degree of the polynomials and the quality of the mesh. So what I'm getting at is that in industrial practice, you can only afford typically to do one mesh of a body. And you'll redo it if you're in trouble. But it's good to have some preconceived notion of what the convergence properties of your system are so that you can go right away to a mesh that will give you your 5% accuracy or whatever is desired. Now, in our academic study of this convergence, we're going to talk first about the mesh refinement, and we'll talk about the h being the average size of the element. P will be the polynomial degree of the displacement field in the elements. And it's been shown that the displacement field in your solution has error of the order of the element size raised to the polynomial degree plus 1. Right away you see that probably the polynomial degree is more important than the element size because of the power of an exponent. Now this large O here means that the error is proportional to this P plus 1. And that means that in the limit, as you go to small mesh size, let's say, that the error divided by the h to the power P plus 1 will go to some constant value. And that therefore there's some sort of a bounding of the error that's involved. Now, when you talk about a specific case, let's say the Turner triangle where you have a linear displacement field, then the error in the displacement field is of the order of the element size raised to the power 2, because P, the polynomial, is 1, and then you add 1. And you look at that and you say, well, that looks pretty good, because if I cut the mesh spacing by a factor of 2, then I'll reduce the error by a factor of 4. In other words, it goes like the square of the mesh size. That's still not quite as good as you might think, because having the element size will create 4 times as many elements in a given domain, because it's a two-dimensional problem. So you really are barely keeping up with the error. You really do 4 times as much work to get 4 times the accuracy. Unfortunately, that's not all the story for the Turner triangle. Although you get reasonable accuracy results on displacements, if you look at stresses, things get worse. Let's go to the general case, first of all, to elastic elements that have stresses that are first derivatives of displacement, and that would include the Turner triangle. Then the derivative knocks down the accuracy, and your error in stress goes to the order of the element size to the power P. So we've lost the unit value in the exponent. Then if you go to structural elements which have 2 derivatives involved in the strain displacement law, you find that the error in stress goes as the order of h to the P minus 1. That looks bad, maybe even hopeless, but it turns out that structural elements use higher degree polynomials, so there's some compensation. Now if we look seriously at the Turner triangle, ask about the convergence on stress, we see that it goes as the order of the mesh size h. Now that's unfortunate, because in a two-dimensional problem, if you have the mesh size, that takes you 4 times as much work and you only get twice the accuracy. So you're on the losing end of things there. And then if we look at an example of a structural element such as the simple Euler-Bernoulli beam, you would find that that's a cubic polynomial in the interpolating function, and then there are 2 derivatives that knock the error in stress to be of order h squared. Now for a one-dimensional beam structure, a rod or a pole or something, this is good, because you then would have the mesh size and you get 4 times the accuracy, or another way to say it is 1/4 the error. But in 2 dimensions it becomes a wash, and in 3 dimensions you start losing, because then you need perhaps 8 times as many elements to get 4 times the accuracy. I've done a small study on convergence using a tapered line element, and this is meant to play off the H and the P convergence. Here I show this single tapered line element, and the area ratio is shown down in the lower right corner. It's varying linearly, but this means that the diameter of the element is varying as a square root with distance along the x-axis. Then I take two such elements using the same end-to-end area ratio of 2 and equally divide, and in this case use linear elements. Here I take 3 linear elements, 4 and 5. So basically this is an H convergence in the horizontal direction. Then in the vertical direction, as we move here, I go from a 2-noded to a 3-noded element so that I use a quadratic function for the interpolation polynomial, then a cubic, a quartic, and a quintic. And so we're getting basically a P convergence as we go downward. Then these intermediate pieces in here are all hybrid types of convergence. There really would be two ways to do this set of solutions. In both cases, I'd like to compare with the exact solution, which is logarithmic, and in which one accounts for the taper of the element in the integration of strain energy. So the two approaches would be to either account for the taper directly in the integration of strain energy or to assume it's a constant area element in each case. But I've decided to concentrate now on the role of the polynomial and the role of the number of elements. So I've decided to integrate exactly in regard to the area distribution. So that won't be a third contributing factor here. And when we get done, we'll compare the 3-noded elements, whether it be 2 linear elements or 1 quadratic element. Then we can also compare the 4-noded versions, and we can compare the 5-noded versions. Now there's an intermediate case here, a hybrid element with 5 nodes also. Let's look at the results of our convergence study. For the baseline element here, a single 2-noded element, our answer is 4% high. Then as we move along this axis to the right with more elements, 2 elements give us only 1% error, 3 elements give us some 0.5%, and 4 elements 0.25%. Now there's an improvement there of somewhere between a factor of 2 and 4 per addition of a degree of freedom. Now that's going to turn out to be modest compared with the P convergence down the vertical axis, because here as we go from the linear element to a quadratic element, we have only 0.121% error, and that's an improvement of some factor of 30. Here again, as we go to a cubic element, the improvement is dramatic again, perhaps another factor of 30. And lastly, the last one that we've done calculations for, with a quartic, we again get that same ratio of about 30 in improvement and converge very quickly. Michael Dungan has helped me with these calculations. Now I did an intermediate calculation here for the 2-element with 2 parabolic interpolation polynomials, and that also had a nice result. One thing you can do is to compare the two accuracies at a constant number of degrees of freedom. For instance, we could compare this 3-degree of freedom model with this one here to see that the P convergence is indeed looking better. We can compare this 4-degree of freedom problem here with this 4-degree of freedom. And then lastly, there are 5-degree of freedom solutions here that I'll roughly outline. I'm not being very accurate on these drawings. So nice little problem to see the trade-off between P and H convergence. Now, you can see from it, however, that there's going to be more and more interest in P convergent finite element programs because of the power. The downside on that is that it's more difficult to develop the elements, and so there will be a certain amount of element development needed, and then extending into nonlinear regions often is tougher as you go to higher and higher polynomials. I've turned our lab problem number 1 into a convergence study by using refined mesh. Here I've used quad 8s and then in increasing refinement until I reach something close to the exact value, 391 megapascals. Remember that the classical value for a doubly infinite plate with a hole in it was a factor of 3 at the top and -1 at the side of the hole. And the -1 would have been in compression. So these numbers are substantially higher than the doubly infinite body, and it shows how the stress has to flow through those narrowed regions, and you get an increased stress concentration factor that way. Now, the quad 8 element in MSC Nastran gives you corner or nodal values, and so we're looking at the stress in the proper site. And so this is basically a mesh refinement, a study of the H convergence. A second study for that lab problem number 1 was done with quad 4 elements. Now Mike Eldred helped me with these calculations. And here the quad 4 has a problem in that it basically gives centroidal stresses. That's its most accurate stress, and I didn't try to get grid point stresses on it. I just used a refined mesh so that the solution that we're getting here is showing not only the effect of the H refinement but also the positioning of the point in question. And we're getting a convergence toward the proper point at the same time we're converging with smaller elements. Now, this set of numbers converges monotonically from below, and maybe partially because of that position error that I've mentioned. We don't quite reach as high a stress as the quad 8 did, even with our finest refinement. And I think I would attribute most of that to the difference in the position that's being measured. Now, between this figure and the previous one, you can also do something like a cross plot and get a little bit of a concept of P convergence. We lack a true absolute correct value, so it would be a little difficult to draw the complete conclusions from this study, but I think there's some nice indications here. Most of the comments that we can make about the preceding 2 figures would have to be considering convergence in the Cauchy sense. That is, how does each of the refinements differ from the previous one? Because we do lack that absolute number for the precise answer. Now let's go on to some convergence criteria that have been known for some years, and these are given somewhat heuristically but are so logical and everyone agrees to their validity and importance that I guess I won't quibble about mathematics. The first is that in order to get convergence to the correct answer, you need to have displacement functions that allow rigid body modes, and I show here the original body in black and then the deformed body in red. Notice that it's a large translation, and of course that is exaggerating the infinitesimal types of translation that we're interested in this course. Likewise here, this large rotation is quite an exaggeration as well. But your assumed displacement field has to allow this, and if you don't, you're going to get in trouble. Secondly, if you pick displacement polynomials, you have to have those that allow constant straining modes. And that would mean that you could perhaps take this body and stretch it, as I've shown here, where the original black square goes into the red rectangle. This would be a sort of a uniaxial type of extension. Over here, though, there's a biaxial type or a dilatation where the square goes into a larger square. Now that would have constant strain both in the, say, the x and y directions. And then thirdly, you like only to have finite strains at the inter-element boundaries. This is a displacement compatibility, or sometimes what's called a conforming element. And it isn't just that the nodes are kept in contact, but all the material on the element edge is kept in contact. So you cannot get a hole opening up, as I have just suggested there. So these are convergence criteria. The first two, in some sense, are the same as a Fourier analysis, where you're asked to keep the long wavelength terms. You know, you wouldn't lightly skip terms in a Fourier series unless you had reason to, because long wavelength information is often dominant in physical processes. So see here these constant translations across the face of the body, or the, perhaps in this case, the rigid rotation involves linear displacement fields. This is important. These are long wavelength things. Then you come next to the linear straining terms that you need to carry. And then it turns out you do not need the higher ones for convergence. You do need these first two sets of terms, and they capture what you could roughly call the long wavelength behavior of the displacement field. Now the third one is a little trickier. It's more of an energy argument that you don't want to lose energy at the inter-element boundaries by having a hole open up or overlapping material. The monotonic convergence that we noticed in the Quad 4 study for the lab problem 1 turned out to be somewhat accidental in that problem, but you can guarantee that under certain conditions. Malash was the first discoverer of this concept, and he stated conditions for guaranteeing monotonic convergence. If your elements satisfy those conditions of conformability, and that is displacement compatibility, and if a sequence of solutions is made with nested grids, that means the subsequent grid patterns carry all the previous boundaries, so you're only adding degrees of freedom, adding new degrees of freedom. You're not losing old degrees of freedom. And then if you use a potential energy formulation, then you're guaranteed to converge monotonically from below on displacements, strains, stresses, and strain energy. And in other words, the model is too stiff, which is similar to the potential energy theorem and as it's carried out in the Rayleigh-Ritz method. So if you are a very formal developer of finite elements and you follow these rules, then you will guarantee that the element is too stiff and that your stresses are too low. Now, an unfortunate thing is that that's not conservative from a design standpoint, because you rather would have stresses estimated too high to give you some warning, you know, a little more caution built in. But nevertheless, people have learned to deal with this. It is a general disadvantage of the displacement method in finite elements, however, which is basically built on virtual work and potential energy ideas. There is a need for a more practical test of whether elements are going to converge or not, and one was produced by Bruce Irons called the patch test. The preceding conditions by Malash that we just discussed are considered sufficient, and that means that they're more severe than really necessary. Now we're going to get into conditions that are more relaxed, not quite as severe. And in fact, you can find that you can show convergence of non-conforming elements. That means even those that have holes or overlapping at inner element boundaries. Now, here's Irons's patch test. If you create an arbitrarily shaped patch of elements and you have at least one internal node, and if you impose displacements on that outer boundary that are consistent with a constant strain field, and if you get the correct stresses out of this element in this patch, element by element, then the element will converge to the correct answer. Now, this is not a mathematical proof here. We're just stating the result. And it's really a practical test because people can do this numerically. And having in their hand a new proposed finite element, a person can build this small patch of elements and see whether the element passes the test. Here's a typical patch. I show a triangular element pattern here with 5 elements and a single internal node. Then if you impose displacements around the periphery that are consistent, say, with a uniform epsilon x, so this is a constant strain in the x direction, which would strain the body as shown at the right, then you would check the stresses that you get in the element for the given material properties, and if they're exact, then you've got a good converging element. Physically, the rationale is that there is no energy lost at the inner element boundaries. Therefore, the energy of the imposed displacement field has to go into the internal strain energy in the body, and therefore, if your internal element model is consistent, you shouldn't have any lost energy anywhere. An interesting thing is that if you go to smaller and smaller elements, and then you can show that the patch test is both necessary and sufficient. So it's a mathematically a precise measure then of convergence. And you must know about the patch test. I was at a national meeting once where there was an older gentleman at an aerospace engineering national convention, and he had developed an element, and he presented it to the board through a half-hour discussion, and it was a rather intricate element that was in some ways controversial. And as he tried to defend his element during the discussion period, one of the first questions was, does your element pass the patch test? And he didn't even know what the patch test was. And I could see the whole audience kind of sag back and start reading their programs, and they really didn't pay any attention further to what he had to say. And I felt kind of bad about that because he'd done a good job, but no one had ever talked to him about convergence ideas and the importance of proving your element's quality in this way. A young man who got his PhD at the University of Michigan several years ago was Bob Sandstrom in naval architecture. And I asked Bob to give a talk at one of my summer conferences. He had a handful of slides, and one of them was the one shown here with the 2 meters. And I looked at that and I thought, oh boy, what's this? After the conference and the evaluations, one of the attendees said this was the best slide of the whole conference, and why didn't we have more like this that really explained things clearly? And it's really true. His effort meter and his accuracy meter, the whole goal in finite elements is to have your effort meter down at a pretty low value and your accuracy meter pretty high. And so I guess Bob really got the idea through. So I laughed about that, and Bob gave me permission to use his meters in my discussions after that. Another graduate student who took my finite element classes live was Leisha Peterson, and she said, Professor Anderson, would you like a convergence study that we did some time ago at General Electric? And I said, sure, get permission and bring it in. And she brought it in, and there's nothing very controversial here at all. It was a study of a compressor of a jet engine. And this has to do primarily with the hub area, and there would also be blades, of course, that would go along with this. Here are several stages of a compressor. The axis of rotation would be down below here. These spin, and these are like hollow discs as they're shown. They found that these compressor stages could be isolated, and it was done actually mechanically by these flexible arms that are pre-tensioned in a way to cause a certain force between the different stages. Apparently this is like a dust cover, this sheet metal like structure here, and then these are like clasping hands here where they overlap and they're tensioned to maintain the tightness of that seal. Well, they decided to isolate one stage of the compressor by this dashed line, and then to use a forced boundary condition on the broken edge of that system. So the stage was isolated, and this axisymmetric model was built, and still it was too big for the kind of problem they were envisioning. They were going to optimize the shape of this structure, and they wanted to run a problem over and over, so they wanted fewer degrees of freedom. So the second windowing in or zooming in was done with this dashed line, and here they put displacement boundary conditions on the cut edge. So that's kind of a nice trick then to see how you can proceed from a larger model to a smaller one by isolating, much as a free body diagram, the region of interest. And then you have to apply either the set of displacements or the set of forces on those cut edges. Three models were made of that final zoomed in area, and they were at different densities. Density number 1 shown here is the coarsest, 2 is the middle, and 3 is the finest. Now these are not nested mesh in the sense that Meloche thought of, because these do not replicate in the following figure. In other words, we don't just subdivide case 1 to get case 2, but rather there are new boundaries developed here that and old ones are lost. So we aren't guaranteed of the convergence in a monotonic way. Also, the element that was used was not necessarily a compatible and fully potential energy generated element, so we won't get the monotonic convergence that we had expected from Meloche's ideas. This particular analysis group had their own in-house finite element code that they used a lot for their own work, and they like to make their models with that code called affine/mass. Now this had to do with axisymmetry cases. So they identified the high stress regions in their problem with that particular code, and those are marked here. Then we'll look at the stresses at those points in the next table. I'll show you the stresses at those 5 critical points. We're interested in these 3 local studies with the coarse, intermediate, and finer mesh density. There's also a global solution, and then the one with this reference code. The stresses that we're interested in actually here descend monotonically as well as here. Here they're ascending monotonically, and so this is what we would have expected from a model that was too stiff. So there's a mixture here, and it's clear that this finite element family that it was used does not satisfy Meloche's criteria for monotonic convergence. And that's quite common because you can have non-conforming elements, for one thing. Secondly, when you go into numerically integrated elements, sometimes there are numerical approximations that will take you away from that potential energy formulation initially. The objective of this study was to find a mesh refinement that would be efficient for doing many, many optimization studies. And so we have to compare the accuracies and the cost of these different local solutions. If I call the coarse mesh the reference and give it a 0 as its percentage change, then the medium solution was 7% more accurate, and then the fine solution added 2% more in the accuracy. And in each case, it roughly doubled the cost to move to those finer meshes. So an engineering and a business decision was made that the optimization would be done at this intermediate level of accuracy because it wasn't worth spending the extra money to get that last 2% of accuracy. Indeed, then, you could do a fine mesh at the very end as a final proof of your design. Problem number 1 is a question I asked in the preliminary exam for our PhD candidates just last term. I proposed that there be a hypothetical element with 3 degrees of freedom as shown. And this was a triangle. It was an equilateral triangle, and each of the nodes could slide in and out along the lines shown. And this was a 3 degree of freedom triangle. So I asked the students, is this a useful element for general use? And discuss its good and bad features. And then use some of the commonly applied criteria to evaluate this element. As a plane stress triangle, this element is pretty bad. First of all, it would have trouble in connecting with the neighbors. Notice when I have 2 adjacent triangular elements such as this, that at a common node, one triangle can only move vertically at that node and the other at this angle here. That would effectively lock up the combined node because of the infinite stiffness in the other directions. It's a little bit of an unusual thing to have to consider such a nodal connection because it's very rare that you restrict your degrees of freedom like that. Another general feature is that with only 3 degrees of freedom, you could represent 3 different kinds of displacement field. One of them we've identified already would be where the 3 nodes moved equally outward, and that would be called dilatation. Then you could have combinations where one moved inward and the other 2 outward, and then that would give sort of a combination of compression and extension. You'd have to look at the stress that would result to figure out what that is, but it's certainly a straining mode. But it appears that there's no possible way to represent any of the 3 required rigid body modes. Remember that this element would have to have translation in the x direction, in the y, and then rotation. And I think if you play around with those degrees of freedom, you'll see there's no way to add those up to get the required rigid body modes. Another problem area for this element would be passing the patch test. If you have an assembly such as shown here and you impose the constant strain field on it by moving the outer boundaries, you'd find that really the elements would lock up and there's no way to get, for instance, in some interior element, a constant strain field. So just the assembly alone would fail there, which we mentioned earlier. Now, there's the paradox for the element developer that if you want to have a triangle in 2 dimensions, Zienkiewicz says that you must represent all 3 rigid body modes, and then you also must represent all 3 constant strain modes. Now that will in fact take 6 degrees of freedom at least, and so really the Turner triangle is the simplest element that is a convergent element, and anything simpler, such as the one that we've proposed here, would fail. Problem 2 will test your understanding of the H convergence and the P convergence. I've created a hypothetical plane stress element that I'll call the amoeba element, and we will assume that there is a 6-noded version, a 10-noded, and a 15-noded version. Now, since this is plane stress, then each of those will have 2 degrees of freedom per node. And I want to set up a test case where we model a certain planar problem and use 100 of the 6-noded elements for one mesh, but use a second mesh with 49 of the 10-noded elements and a third mesh with 16 of the 15-noded elements. So we're playing off one against the other on P and H convergence. And the question is, which of those models will have the least error in stress? And we'll assume that the quality of the mesh in each case is similar. In other words, one of them isn't very badly done with a lot of distortion and a lot of the elements all bunched up in one corner. If you cast this into non-dimensional form, it could help a bit in the error comparison. To solve this problem, we need to know something about the polynomial nature of the interpolation functions, and then we need to know something about the average element size. We'll start with the polynomial discussion, and for a 6-noded element, there will be 6 coefficients required to define the u displacement, as well as 6 more for the v displacement. If we concentrate on the u displacement, we would need such a polynomial with 6 generalized coordinates, and that luckily turns out to be a complete quadratic. The 10-noded element will require 10 generalized coefficients, and if you lay those out, you find that you can do that with a complete cubic. Lastly, the 15-noded element, if you put all the 15 generalized coordinates out, will turn out to be a complete quartic. Now, as you can see, I've conditioned this problem a priori to give us rather nice functional behavior here. So whoever developed the interior workings of the amoeba element would undoubtedly use a complete quadratic, cubic, and quartic in that development. Now we need to think about the average element size. This is a 2-dimensional problem, and there are 3 models of the same geometry. If we think just in our minds of a square region, then the size of the element is going to be proportional to the square root of the number of elements. That's because we need to, in our model, we need to build our mesh in 2 directions. And so therefore, I'm going to use in the estimate for error, I'm going to not worry about the dimensions on this, but I'm going to say the error is proportional to here was the h value, which is proportional to 1 over the square root of the number of elements, which would be the square root of 100. The first model used quadratic elements and a lot of them, and that number comes out to be 1/100th. The second model used 10-noded elements. There were 49 of them, and the average mesh size or element size would be 1 over the square root of 49 in a non-dimensional way, with the complete cubic polynomial, and that gives 1 over 343. Lastly, the 15-noded element, the h is proportional to 1 over the square root of the number of elements, which was 16, and that was a quartic polynomial. That number comes out, this one, 1 over 256. So the winner is the intermediate complexity element and the intermediate mesh size. And so I think I contrived this ahead of time to keep people from guessing which one was going to win. And we had a pretty tight race between P and H convergence. And in this case, neither one won.